Okay, we're going to continue on here, chapter 9. I think we just got right into the beginning of it. So again, in this chapter, we're going to talk about stoichiometry, really, which are calculations that are based off of equations. As we talked about, I think at the very end last time, again, a really important sort of calculations used in these is going from grams to moles, and again, moles back to grams. And once again, that is, again, the molar mass from the periodic table that you get from underneath the elements, and basically gives you how many grams per mole that you could use basically as a conversion factor to do that. So if you do have grams, do a little dimensional analysis. Again, grams on the bottom, moles up on top, and they will basically cancel out the grams. If you have moles, again, multiplying by the molar mass, using it as a conversion factor, the moles will cancel and give you grams. So again, very commonly used in these calculations. A lot of times at the beginning and the end of the calculation, you very often will use sort of molar mass to do so. So let's talk a little bit about sort of the stoichiometry here, which I don't think we got too far into last time, but the idea here is when we look at a balanced equation, we can look at the coefficients as the numbers of, for example, in this case, molecules of H2 and molecules of O2 and H2O. And we could use a relationship which is really just the coefficients to get that. We could say 2 molecules of H2 react with 1 molecule of O2, gives us 2 molecules of H2O. The really stoichiometry sort of relationship that we use the most is really was referred to sometimes as the mole to mole relationship. And that also is just using the coefficients. So we could say for every 2 moles of H2 we put in there, we also need to put 1 mole of O2 and 2 moles of H2O will be produced. The last one we don't really use too much, but this is a conservation of mass because, for example, here hydrogen weighs the same on both sides. And because we have the same number of hydrogen atoms on both sides of the reaction, we'll have the same mass of reactants and products in terms of all the elements that are present. So when we do stoichiometry sort of calculations, much like the experiment we did way back whenever that was, before all the holidays, where we produce how much product. That's a very common sort of calculation that we do, which is trying to figure out how much product you're going to produce. If you start out with a certain amount of reactants, we could also figure out if we know how much product that we actually did produce in a reaction, we could sort of back calculate and figure out how much reactants we started with. And one thing is important when you think about sort of stoichiometry sort of relationships. Sometimes people, when they look at an equation, think that you have to do these type of calculations by kind of going across the arrow, and you can definitely do that. You could go from reactants to products or products to reactants, but you could also do the same type of calculation we're going to be talking about between 2 reactants. You could also do it between 2 products, so you don't necessarily have to cross over the arrow or anything like that to do these type of calculations. Now, the units that we'll see, and we'll see some different units as we go through some other chapters as well, but in this one, probably moles and grams are going to be very common units. Later, when we talk about gases, liters is also a common unit. Molarity and volume for solutions is also a very common sort of unit as well. And the mole method is this idea that everybody is related to each other, thank you, based on the coefficients that we have in the equation. It gives us sort of the proportion of everybody that needs to react to be able to produce a certain amount of product, or again, sort of figure out backwards how much to do it. Now, these are the steps that you can follow for a basic stoichiometry problem. And we're going to talk about kind of basic stoichiometry problems and a little bit more complex problems a little bit later on. But the first thing you want to do is make sure that you write the correct formulas of the reactants and products. And this would be a situation where you're just given everything in words and you need the equation. And really, as we'll talk about, nothing works right for stoichiometry sort of calculations if you do not have a balanced equation. So to do that correctly, you do want to make sure you start with the right numbers of formulas of the reactants and products. Then you want to balance it. So as we talked about when we talked about balancing equations, that should always be the order that you do it, which is get all the right formulas and then go back with the coefficients and balance the equations. Once you do that, you want to convert whatever they give you basically to grams, and then you want to go from grams to moles. That is usually your step. The reason for that is step number 4 is you want to do the mole to mole relationship from the equation. And then on the back end here, a lot of times you'll be in moles and want some other unit. And a lot of times that's also going to be grams on the back end. So molar mass is used on the back end. So really for basic sort of problems, there's really 4 steps that you could just follow. One is you want to make sure always you have the balanced equation. You want to take whatever they give you, get it to grams, and then convert grams to moles. Most likely that's going to be a molar mass is going to be used. You want to go to the equation and do the mole to mole relationship. And those are between 2 things that you're interested in. And lastly, you should always be in moles at this step. And if you need some other unit you want to convert it into, also molar mass, very commonly used here on the 4th step as well. So if you follow those steps sort of in order, you never want to undo something. So if something is done for you, all you want to do is go forward in those steps. Don't go backwards, and it should get you hopefully to the right answer when it's all said and done. So let's take a look at an equation. So if we have this equation, from this one equation, we could come up with a lot of relationships just using, again, the coefficients in the balanced equation. So from this equation here, we could say that we have, for every 2 moles of CO we put in there, we basically need to put in there 1 mole of O2. And again, that is just simply the coefficients. For every 2 moles of CO we put in there, we would expect to get out here 2 moles of CO2. And for every 1 mole of O2 we put in there, we should also get out 2 moles of CO2. So from this one equation, we actually have 3 equalities, right? So these are equalities. These are what are sometimes referred to as stoichiometrically equal to each other. They clearly are not equal to each other in terms of number because 2 does not equal 1. But they are equal to each other in terms of, for this particular reaction, that is the proportion of things you need to throw in there to get this reaction to sort of work. Now, because those are equalities, just like any type of equality, you could write 2 conversion factors. So for example, we could write 2 moles of CO over 1 mole of O2. Or we could flip it around, 1 mole of O2 over 2 moles of CO, and that comes from this equality right there. For the second equality, we could also write 2 conversion factors. 2 moles of CO gives us 2 moles of CO2, or you could flip it around, 2 moles of CO2 gives us 2 moles of CO. And lastly, for this last equality here, we could also write 2 conversion factors. 1 mole of O2 gives us 2 moles of CO2. Our 2 moles of CO2 gives us 1 mole of O2. So from this one equation, we basically have available to us 6 different conversion factors that we could use in a stoichiometry problem. And really, that is pretty much what stoichiometry is. It's really just a conversion factor. And instead of looking up the conversion factor like in a table or something like that, you just get it from the actual equation. So that is where you basically get it from. And the reason for that is in most stoichiometry problems, you're given information about somebody in that equation that you're really not interested in, but you're interested in somebody else that's in the equation. So you need a conversion factor to go between those 2 things. And again, we get it from there. Will you use all 6 in a calculation? I hope not, because you probably are doing it wrong if you are. You should only probably use 1, probably in most calculations that you do. So you would just usually need to use 1 of these that are appropriate in a calculation. So for example, if we had a problem like we produced 12.5 grams of CO2, and we want to know how many grams of O2 did we start with. So in this case, what we would want to do is kind of follow the 4 steps. First step is to balance the equation, which obviously it is, so that is good to go. Step number 2 is to convert to moles. And in this particular case, we have 12.5 grams of CO2, which means we do need to convert it to moles. So we would need to go to the periodic table and find like carbon, which is 12.01. We need to find oxygen, which is 16. And we would need the molar mass here to do that for CO2. So if we did that for CO2 from the periodic table, there's 1 carbon at 12.01. There are 2 oxygens at 16. That is going to get us 4401 grams per mole as the molar mass of CO2. We're going to use that as a conversion factor here. So the number, by the way, always stays with the grams part, and it's always per 1 mole when you calculate the molar mass. So if I take my 12.5 grams of CO2, I want to use my molar mass where grams will go on the bottom here so that they cancel out, opposite location. And moles of CO2 would go up on top. Again, we're multiplying, right, and dividing here. So our grams of CO2 will cancel, and that's going to get us here 12.5 divided by 4401. It's going to give us 0.28403. I'm not going to round too much just yet. And that is moles of CO2. Any questions so far on that there? Now, the third step is actually the stoichiometry step, and this is our mole to mole relationship. So what relationships should we be looking for? Well, we should definitely be looking for in the equation what was given to us, which in this case is CO2. And the second thing that we should be looking for is what we're trying to find, which in this case is O2. So we do want the relationship from the equation of those two guys. And we did that earlier. So earlier we saw that 1 mole of O2 would give us 2 moles of CO2. And again, that comes from the actual just coefficients from the equation. That gave us an option of basically 2 conversion factors here, right? So those are our 2 possible conversion factors that we could use. So now we're going to do the calculation, and what we're going to do is basically take the number we had before, 0.28403 moles of CO2. Once again, I want CO2 to go away. So we want CO2 in the opposite location. And in this case, that is the conversion factor here on the left. We'll do that. Again, that's going to put the CO2 on the bottom. Bless you. And the O2 up on top. And this is going to be the big stoichiometry move right there. There it is. We're basically going to divide this guy by 2. And if you got an answer, 0.14201 moles of O2. Any question on that part of the calculation? Now, if I wanted my answer in moles, I would be done. I basically could get the right sig figs and put a box around it, and I would be done. But I'm not interested in moles. I am interested in grams, which means I do need to do the 4th step, which is convert to grams. Again, I'm starting with moles, and I want grams, so I do need the molar mass. We do need to remember that we're no longer at CO2, we are now at O2, right? So I need to go back to the periodic table and get my molar mass of O2 in this case, and that would be 2 times 16, giving me 32 grams per mole. I'm going to use that as my conversion factor. I'm actually going to do it right here, I think. And in this case, we want moles on the bottom so that they cancel. And we want the 32 grams up on top. This is going to cancel. And that would get us here about 4.54 grams of O2. So basically what was needed here is you need to put in there 4.54 grams of O2. And if everything went well, that should get you your 12.5 grams of your product. First off, any questions on any of those steps? Yeah. You can. That's exactly what I was actually just going to say. So I did it here in the steps so you can see all the steps. But if you wanted to go from here to here to here to here all in one without getting an answer, that's perfectly fine. That's actually how they prefer you to do it here at the school, but I don't really care. You can do it either way. But you can definitely do it all in one calculation. I would say if you lay up an answer in between like I did, try not to round too much till the end, and then at the end, kind of do some rounding. But absolutely, you could go from one conversion to the next, to the next, to the next. Other questions? Okay. Yeah. I did on this one because the only number that we had 3 sig figs, right? The 12.5. So that's why I went with it. Yeah. All right, so let's take a look at one here. Why don't you try this one? Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of H2 can be formed by the reaction of 5.32 moles of lithium with water? So again, follow those 4 steps. Balance the equation. Convert to moles. Mole to mole relationship. And moles to some other unit. Okay, so let's take a look at this. So in this one, we actually don't have the equation given to us. We have it all in words. So once again, a reminder, we do want to start with the right formulas. So lithium metal would be Li. React with water, which would be H2O. To form hydrogen gas, remember hydrogen gas, like nitrogen, oxygen, all those others are H2 in this case. And lithium hydroxide looks something like this. Obviously, now that we have all the proper formulas, we want to make sure that we do balance it. And in this case here, I think we want like 2's is on the menu here. 2, 2, 2, 2, I think. Yeah. How about 2's everywhere but one place? There we go. Now that we are balanced in this case, that's obviously step number 1. We are given that we are starting with 5.32 moles of this guy, and we want to get over here to figure out how many moles. So step number 2, convert to moles. It's already done for us, so we don't need to uninvent the wheel there. We already did that. So we just need to then go to the next step, which is our mole to mole relationship. So in this particular case, obviously lithium, what they gave us is what we're interested in. And obviously what we're trying to find is another thing we're interested in. So step number 3 here would be our mole to mole relationship, which again, from the coefficients tell us for every 2 moles of lithium that we put in there, we get 1 mole of H2 out. That again gives us our 2 possible conversion factors that we could use. And taking our number there, 5.32 moles of lithium, opposite to cancel, which means this would be a good conversion factor on the right there to use. That's going to get us here 2 moles of lithium and 1 mole of H2. Moles of lithium are going to cancel. Going to get us here 5.32 divided by 2. 266, it looks like 2.66 moles of hydrogen. In this case, that is actually the answer we're looking for because we're looking for it in moles. We do not need to actually do step number 4 in this case because we're actually looking at it for moles. If we did want to go to grams, we again would need the molar mass here of H2 from the periodic table if we wanted to get grams in this case. This, by the way, would be the theoretical yield in moles. theoretical yield is your maximum amount of product that you should make based on how much you start with in terms of reactants. Any questions on those steps? Again, you don't necessarily have to write the conversion factors or all those things, but again, just doing it so you could see it there. All right, so let's try another one here. Is that it right there? Yeah. In this case, we're going to use the same equation and reaction. We're going to start with 81.75 grams of lithium, and we want to know how much hydrogen grams we would produce. So lithium is 6.941, and hydrogen 1.008. All right, so again, follow those 4 steps. A little balanced equation, a little convert to moles, some mole-to-mole relationship. Okay, let's take a look. So again, I'm going to follow this 4 steps. So step number 1 was done for us, is balance. Again, in this case, we're taking 81.75 grams of lithium, and we want to know how many grams of H2 in this case. So step number 2, which is convert to moles, we do need to do. And again, we could get that from the periodic table there. So for lithium, it's 6.941 grams per mole. A reminder, as we talked about last time, whenever you are calculating the molar mass, it should be done by the formula alone. You should not use the coefficient or anything like that in the molar mass. That's why it's always 1 mole as the molar mass, and the grams stay with the number part of it there, but never use the coefficient in a balanced equation doing the molar mass. So here, again, just set an up-dimensional analysis way. Again, opposites cancel, which means we do need grams on the bottom here, and the moles of lithium up on top so that they cancel. Once again, you don't necessarily have to get an answer at this point, but if you did, you would get 11.778 moles of lithium. We're then ready for our 3rd step, which is the mole-to-mole relationship. So going to the equation, we'll find again the 2 things we're interested in. One thing is what they gave us. The second thing is obviously what we're looking to find. That's the same relationship we used previously there. 2 moles of lithium gives us 1 mole of H2. Again, nothing more than just the coefficients where we're getting the numbers from. That again, you don't necessarily have to write the conversion factors, gives us an option of 2 conversion factors to use. And again, we want to use the one which will get rid of what we don't want and leave what we do want. So opposites again cancel. So taking our number from above, or if you just continue on with the calculation, lithium mole should be up on top, which means we do need to use the ones with it on the bottom here. And 1 mole of H2. That's the stoichiometry part that's going to move us from lithium to hydrogen using the equation as a conversion factor. And that's going to get us, we'll call it 5.8889 moles of hydrogen. This would be our theoretical yield here in moles, but in this case, we do want grams, which means we do need to do the 4th step here. We also need to remember that we have now converted over to hydrogen, so we need to go to the molar mass for hydrogen. And again, that is 2 times 1.008, going to give us 2.016 grams per mole. Again, we're going to use that as a conversion factor. 5.889 moles of H2. Opposites cancel, so moles on the bottom here and grams up on top. They cancel, and that's going to get us back to 11-ish, I think. 1187 in this case. Grams of H2, which would be our theoretical yield in grams. And again, same 4 steps, balance the equation, convert to moles, mole-to-mole relationship, and our moles to some other unit. Once again, as was questioned earlier, you absolutely could just roll from this calculation to this calculation to this calculation and get your answer at that point without any sort of answer in between. Any questions on that? Again, here 4 sig figs based off of the only number, which was 81.75. That 4. Yeah. Any questions on those steps there? Yeah. All right, try a couple more here to make sure. That's the one we just did, so hopefully they get the same answer. That would probably be good. All right, let's try this one here. If 765 grams of C6H12O6 is consumed by the body, we're looking for maybe, nice highlighting, we're looking for how many grams there of CO2 in this case. Some numbers that might be helpful. Carbon is 12.01, hydrogen 1.008, and oxygen 16. All these four steps, we already have an equation. There's some coefficients. We're going to hope it's balanced here. We're starting with 765 grams of this guy. We want to know basically how many grams of CO2 here. So second step here, we do need to convert to moles. And a reminder that you may be given units of any type of unit. You just want to get them to grams and then grams to moles basically for the second step. So it may require multiple conversions sometimes, but usually you're going to start probably with grams. So we do need the molar mass there of our C6H12O6. Go to the periodic table, 6 times our 12.01 for our carbon, plus 12 times our 1.008 for our hydrogen, plus 6 times 16 for our oxygen here. And that is going to get us 180.2, looks like. We will also need on the back end some molar mass there of CO2. So might as well grab that while we're up here. So carbon dioxide here, 12.01 grams per mole for the carbon, 2 times 16 there for our oxygen, giving us 4401 grams per mole. All right, so we are ready to do this. We're going to go 765 grams of our C6H12O6. We're going to do step number 2 here and convert it into moles by using the molar mass. Once again, grams do need to go on the bottom here, and moles will go up on top. And here the grams will cancel. So again, just to show you, obviously you can do it all together. That's how I'm going to do this calculation. I can see now that I have moles of the C6H12O6. Now I'm ready for step number 3, which is go to the equation and find those relationships there. And from the equation, we can see that for every 1 mole of C6H12O6, we get 6 moles of CO2. Again, setting it up in dimensional analysis here, we have the moles of the C6H12O6 on top, which means opposite to cancel. So we'll put those guys on the bottom, and obviously our moles here of CO2 up on top. That is going to cancel our moles of the C6H12O6. We're now in moles of CO2. But we do want grams, so we do need to do the fourth unit conversion here, and we'll use our molar mass here to do so. And once again, setting it up like this, we could clearly see the moles of CO2 are up on top. So again, opposite to cancel, moles of CO2 on the bottom, and 4401 grams up on top. The moles will cancel. Once again, multiplying what's on top, dividing by what's on the bottom. And that's going to give us basically 765 times 6 times 4401 divided by 18, not 18, 180.2. There we go. Going to get us here, looks like 1121 grams of CO2. And sig fig wise, maybe 3 sig figs. So maybe 1120 grams of CO2 there might be on order. Yeah. That again would be our theoretical yield in grams. Bless you. And again, it is the same 4 steps. Step number 1, balance equation. Step number 2, convert to moles. Step number 3, do the mole-to-mole relationship. And step number 4 here, moles to some other unit. Just like at the beginning, you may be given the information in some other unit than grams. at the end, they may ask for an answer in some other unit besides grams. So maybe you might have to do multiple conversions at the end. But usually grams at the end is usually very common. Any question on any of those steps? Yeah.
Molar mass of C612H12O6.
Mhm.
Do you have that number or is that the number?
Yeah, so in general, when you do not significant figures, when you do molar mass, that's what I'm gonna spit out there. When you use molar mass, usually 4 significant figures is what you round to. Yeah, yeah, and usually when you take it off the periodic table as well, 4 significant figures is usually what you want to take, and usually 4 significant figures, kind of general rule of where you round to in terms of significant figures for molar mass when you're calculating it. Yeah, and yeah.
You're doing everything like that and you don't really see what you got.
Yeah.
Oh, actually, never mind. Okay.
Okay. Yeah, so for me, I'm okay if you want to do it like that. Obviously, they would like you at the school to do it kind of like that, all one calculation is kind of what they want you to do here. I'm okay if you want to break it up into the individual parts, just don't round to the end. But just know as you continue on, sometimes they want you to kind of do it all in one kind of calculation. Other questions on that? So these are basic stoichiometry problems. And again, if you follow those 4 steps for these problems, you should be in good shape in terms of getting to the right answer. All right. Hopefully they got the same answer here on this one here. I'm gonna skip that one actually. We're gonna then talk about limiting reagents. And limiting reagents is the idea that whenever you do a reaction, there's always going to be somebody that gets used up first in the reaction in terms of the reactants, and there's somebody that you'll have plenty of. So that brings us limiting reagents and also what is sometimes referred to as excess reagents, or some people call them reactants as well. And based on the stoichiometry, not all reactions get used up equally. So there is a limiting reagent, which is the one that actually gets used up first in the chemical reaction. Now, the reason that this is really important is if you just take a kind of a simple example, if you take A plus B to make A and B together, clearly you need both of those to make your product. Now, let's just say that A was our limiting reagent and B was our excess reagent. What that means is at some point when this reaction is happening, you basically will run out of A. And the reason that's important is once I run out of A in my example here, is there any way I can make any more product? No. And it's always the limiting reagent that actually determines how much product you can make, because basically once it's gone, there's no chance at all that you can make basically that product. So it is the limiting reagent that determines how much product you can make. Kind of like hot dogs and hot dog buns, right? They sell you like 10 hot dogs if they sell you only 8 buns, right? So you're always short, right? Like you got to buy an extra bag of buns. And then you're like, I got extra buns and I got to buy more hot dogs. It's a never ending cycle of buying and using as best. Now, as I mentioned, the excess reagent is the one that you have plenty of. So the excess reagent you'll actually have plenty of, and you'll have some left over when the reaction is done. And part of the calculation sometimes that you're asked to do is to figure out, for example, how much of that excess reagent that you'll have left over when the reaction is done. So if we were going to make some workout buddies here, obviously we need one of each. And you can see here we could pair up 1, we could pair up 2, we could pair up 3. At this point, we are out of guys. That means over here these are our limiting reagents. Over here would be our excess reagents. And as I said before, you can also figure out how much excess reagents you have left over. So obviously at the end of pairing everybody up, we have 2 people left over, and we could actually figure out how much is left over in this sort of reaction. If this was a reaction, obviously at no point, once we run out of guys here, There's no way to put everybody together and continue to make sort of partners at this point. So let's take a look at a reaction here and just to try to explain how you do these calculations. So first off, when we do these limiting reagent calculations, there's actually, I'll be honest with you, there's like 3 or so different ways you can actually do these calculations. So I'm going to show you one way to do it, and I'll explain to you probably another way, which nowadays people like to do a lot, but I'll explain to you sort of the differences of them. But the way we're going to kind of approach it is actually the same way that we do our basic stoichiometry problems. We're going to still kind of balance our equation. We're going to still convert to moles. And pretty much no matter which version of doing these problems you do, that's pretty much always the first 2 steps no matter what. But right around here, we're going to determine the limiting reagent. And right around here, we're going to kind of take a little short break and determine the limiting reagent. Then we're going to pick back up, and using our limiting reagent, we'll do our mole to mole relationship, and then we'll do our moles to some other unit. So really the same sort of 4 steps, except that we need to do one small calculation to help us determine which one's the limiting reagent. So by the way, that is how you need to do that, just so you know. You have to do some type of calculation to determine which one is the limiting reagent. So a very common error that sometimes people make is they just think it's a smaller number. And that's always the limiting reagent, and that is not always the case. So you do have to actually do some type of calculation to determine which one is the limiting reagent. So let's just say in this experiment here, we have this reaction and we're mixing 3 moles of sulfur. Actually, I did it backwards. We're doing 3 moles of fluorine actually there. We'll do what it actually says, might be good. We have 1 mole of sulfur and 3 moles of fluorine in this case. All right, so first off, we want to balance the equation, which it already is. We want to convert whatever they give us into moles. It actually already is. So just like before, if it's already done, we don't need to undo it. Now, you could have been given grams of each of these, and you would have needed to convert to moles. So just like we did in the previous problems, but in this case, they were done for us. In this case, we need to determine which one is the limiting reagent. So we do have to do that step. By the way, the reason we know this is a limiting reagent problem is we are able to get to moles of each reactant. That is how you know that this is a limiting reagent problem. You need to figure that out is whatever they give you, you can get to the moles of each reactant. And that is the key to know that that is a limiting reagent problem. If you think about the problems we did previously, we had just like one piece of information, right? We knew how one reactant, or maybe we knew one product, but we just knew one piece of information. We weren't able to get the moles of each reactant. And that's how you know that you have a limiting reagent situation in that case. So in this case, we definitely have moles of each one, so we know we're there. So to do the calculation to figure out which one is our limiting reagent, this is one of 2 calculations you could do. You could decide, I want to know how much fluorine I need to use up all the sulfur in this case. So basically what you're trying to figure out is if you want to use up one of your reactants, how much of the other one did you need? So you could think of these numbers up here as our starting amounts, right? So these are like our starting amounts of each of these guys. That's how many we have. So if I did that, I'm going to go with my 1 mole of sulfur. I am then going to do a mole to mole relationship from the equation between sulfur and fluorine. And from the equation, that is 1 mole of sulfur gives me 3 moles of fluorine. So I'm just going to do a basic small little calculation here between the 2 reactants, a little stoichiometry calculation. And that's going to tell me in this particular case that I would need 3 moles of fluorine. right? That is not the numbers I want to start with, huh? I should actually use the right numbers. I'm sorry. That's really bad. Let me, I felt like those numbers weren't right, so let me just try that out just real quick here. Let's actually use the numbers that are on there. That's 4 and 20. That seems better. Let me try that again. There we go. Should have slid it over a little bit more. Let's try this one more time here. All right, so we have 4 moles of this guy and 20 moles of this guy. There we go. Let's see that. All right. So we are going to still do our calculation, and from the equation, we see 1 mole to 3. We're going to start with 4 moles of sulfur. This is going to come out better, I think. There we go. We're going to do 1 mole of sulfur gives me 3 moles of F2. So we're just going to do a basic stoichiometry calculation between the two reactants. And that's going to give me 12 moles of fluorine is needed. Yes. It was actually the problem. It was like, it would be like a problem where they said, hey, you started with 4 moles of this guy or 20 moles of this guy, or, 10 grams and 15 grams. So it'd be like given to you in the problem. I'm going to answer your question in 1 second, I think. Yeah, let's just hang on there. So if we do this, what this calculation says is if we started with the correct numbers here of 4 moles of sulfur and 20 moles of fluorine, I would need 12 moles of fluorine to do that. What I then would want to do is actually compare how many moles of fluorine I started with. I started with 20 moles. I would only need 12. Do I have enough fluorine in this case? I do. And that would tell you that this is your excess reagent. The nice thing about this is by default, if you could determine which one is your excess reagent or which one is your limiting reagent, the other thing is happening to the other guy. So that would be by default, this guy is your limiting reagent because I was able to figure out the other guy was my excess reagent. Now, to answer your question, you don't have to do both of the calculations or both of the reactants, but you could choose either one. So the other calculation you could have done to figure out which one's the limiting reagent was you want to know how much sulfur is needed to use up the fluorine. So you could have done the other one. So for example, that would mean in this case, we would start with our 20 moles of fluorine. We would use our same relationship, just flipped around. So 3 moles of fluorine on the bottom, 1 mole of sulfur up on top. And that would get us here, 20 divided by 3, 6.67 moles of sulfur is needed. We would then compare that to how many moles of sulfur we started with. And in this case, I would need 6.6 moles. I started with 4. Do I have enough? I don't, right? In this case, I do not have enough. So that tells me is the limiting reagent. So it doesn't matter. You don't actually have to do both of those calculations. You could choose either reactant, but you do have to do one of those calculations to determine which one's your limiting reagent. And once you determine which one is your limiting or excess reagent, then the opposite thing is happening in this case. So to answer your question, you could do either one. It doesn't really matter which one you start with. But you do have to choose one. And again, it will tell you either it's limiting or excess in that case. Yeah.
Wait, I thought you were saying that there's not enough sulfur. We have 6.67. We start.
We need 6.67 moles to do that, but we only started with 4, right? So 6 is obviously more than 4, so you don't have enough. As opposed to when we looked at the fluorine, we needed 12 moles of fluorine, but we're actually starting with 20 moles, so we got plenty of it, right? We're going to have some left over at the end. So that little calculation, one of those two is what you need to do right around here to determine your limiting reagent. Now that we determined that it is our sulfur that's our limiting reagent, we want to continue on with our 4 steps using the limiting reagent. And it's important that you go back to the starting amount here of your limiting reagent. And that's what you would then do is you would take your 4 moles of sulfur And now you could actually figure out how much product you would form. 1 mole of sulfur will give you 1 mole of SF6. And that would tell you in this case you would form 4 moles of SF6. That would be your theoretical yield in moles. Obviously, if you wanted grams, you could do the 4th step. We won't do it here, but you could use the molar mass from the periodic table, just like we did in the previous one, and get to your grams if you were looking for grams of SF6. So you could follow the same 4 steps that we did on a basic stoichiometry problem. You just got to take a moment and do one small calculation to figure out which one's the limiting reagent. Now, first off, any questions on that there? Now, another common calculation is, our question is, how much of your excess reagent would you have left over? So sometimes you're asked how much of your excess is left over. And we could do that really easily based on our calculation, because if we actually did this calculation, we know that in this reaction, we would need to use up 12 moles of our fluorine. And we know that we started with 20 moles of our fluorine, right? And if we use up 12 moles, which is what we need, we would have roughly 8 moles of fluorine left over, which then you could also, if you want to know how many grams that was, you could use the molar mass of fluorine to get to grams of fluorine that would be left over. So that is also a very common sort of question, which is, not how much you're going to produce, in addition to how much you're going to produce, how much of that excess reagent is left over. Now, for example, if you chose to do this calculation instead of the sulfur one, you would then at that point have to go back and actually do this calculation to figure out, how much of your excess reagent is left over. So that little bit of doing this calculation it's a good thing, because it'll allow you to answer those questions of how much of your excess is left over. First off, any questions on that there? So this is a good way to do it, and the way we'll kind of do it here. The alternative way to do it is basically you would take, for example, here we had our sulfur and our fluorine, right? You would do 2 separate calculations. One starting with sulfur, going from like grams of sulfur to moles of sulfur to moles of SF6 to grams of SF6. And then you would do the same thing. You would start with the grams of fluorine. You would go to moles of fluorine. Then you would go to moles of SF6 and grams of SF6. You essentially would do 2 basic stoichiometry calculations using each reactant, going to the product of your choice there that you're trying to find. And then whichever one would produce the smallest grams of product is your theoretical yield and your limiting reagent. So that is a very popular way that people teach it these days, is just to do 2 separate calculations, one from each reactant to the product. Whichever one produces the least amount would be your theoretical yield, and also that would be your limiting reagent. Now, nothing wrong with doing it that way. Again, if you were asked a question like how much of the excess reagents left over, you would then have to go back and do a separate calculation to figure that out. So it's really your preference, whichever way you want to do it. I don't really care. I would say probably these days, this is very commonly how people are taught. It's just to do 2 separate calculations. But the benefit of sometimes doing it the way we were just doing it is it can help you with those type of questions of how much excess reagent is left over and stuff like that. Like I said, there's actually 3-4 different ways that you could kind of solve these type of problems. Any questions on that? And obviously when you're doing this step here, this would just be the same 4 basic stoichiometry steps we did previously. You just have to do 2 calculations to figure it out, which one you would just throw away at the end that you wouldn't need that number or anything like that. Any questions on that there? All right, so why don't you try one here? I'll just scroll this across the screen. All right, why don't you try this one here? We're going to do 6.83 grams of iron react with 9.34 grams of sulfur. Which of the two is the limiting reagent? And calculate the mass of iron 2 sulfide produced. Iron is 5585. Sulfur 3207.